Hi, my name is Juan Manuel Perez, and today we are going to explain nuclear physics. So, nuclear physics is the field of physics that studies atomic nuclei and their constituents and interactions. First of all, we're going to talk about discrete energy and radioactivity. It all started with the line spectra, as the light from a hot metal has a continuous spectrum and it changes with the different metals. Planck found out that for some metals, the classical physics could not describe what was happening to the light as the results given were an ultraviolet catastrophe. Therefore, in 1905, according to Einstein, light travels in discrete quantized packets of energy, known as photons, where he introduced the photon energy, showing a low energy in a long wavelength and low frequency, and a high energy in a short wavelength and high frequency. Rutherford Goldfield experiment studied in more detail the structure of the atom, and it led to a model of the atom with the following characteristics. The atom consists of a positively charged nucleus around which the negatively charged electrons exist. Most of the mass of an atom is contained in the nucleus. Therefore, this is an unstable system, because accelerating charges, in this case the electrons, emit electromagnetic radiation caused by the existing electrons that change in the energy levels. Atoms are electrically neutral unless sufficient energy is supplied to the atom. The nucleus obtains its positive charge from protons. Each proton has the same magnitude of charge as the electron, which we refer as the same elementary charge, E, and has a value of 1.6 times 10 to the power of 90 to the negative 19. The proton has a charge of positive E, while an electron has a charge of negative E. A nuclide which has excess nuclear energy is unstable and will release this energy in a process known as radioactivity, thereby emitting ionizing radiation composed of any of the three different particles: alpha particles, beta particles, or gamma particles. In alpha decay, a nucleus emits an alpha particle, which is a helium-4 nucleus. In this radioactive decay, the initial nuclide, often called the parent nucleus, decays into a different nuclide called a daughter nucleus, which has 2 fewer protons and 2 fewer neutrons than the original particle, such that there is a transmutation from X to Y. There are two types of beta radiation. In beta minus decay, a neutron decays into a proton which has a slightly lower mass than the neutron by emitting a beta minus particle, which is an electron, and an electron neutrino. Meanwhile, in beta plus decay, a proton decays into a neutron while emitting a positron, an anti-electron which has a charge opposite to that of an electron, and an electron neutrino. In a gamma decay, an excited nucleus transfers its high energy photon with frequencies in the gamma region of the electromagnetic spectrum. This radioactive decay does not result in a transmutation. There is no change in mass nor atomic number. Therefore, radioactive decay is a random process in the sense that it is impossible to tell which of the nucleides in a radioactive sample will decay. All we can claim is a statistical measure for the decay of the entire collection of radionuclides in the sample. The rate of radioactive decay is the number of radionuclides in the sample. Assuming a decay where the daughter nucleus is stable, the number of mother nuclei decreases exponentially, while the number of daughter nuclei increases to keep the number of nuclei in the sample constant. An exponential decay curve may be characterized by its half-life. Half-life is the time interval for half of the radionuclides to decay. Now we are going to talk about nuclear reactions. The equivalence of matter and energy will be the driving formula for this subtopic. It is convenient to write our masses with this in mind. According to Einstein's theory of special relativity, a mass is equivalent to an energy. Mass defect of a nucleus is the difference between the sum of the masses of its constituent parts separately and the mass of the nucleus. And the binding energy of a nucleus is the energy required to separate it completely into its constituent parts. It is the energy equivalent of the mass defect. There we can see the three formulas. Here we can see the average binding energy per nucleon graph, where it shows that there is a sharp rise in binding energy per nucleon from hydrogen, with zero binding energy as the mass number increases. The curve has a maximum at mass number 62 of about 8.8. It is a rare isotope, it is nickel, and it has the highest binding energy per nucleon. The curve slopes down only gently after the peak, falling less than 1.5 mega electron volts from a mass number of 62 to 238. The higher the binding energy, the more energy is associated with the nuclei. In other words, reaction in which the products are higher up the binding energy per nucleon curve will release energy. This is analogous to the creation of stronger bonds in a chemical reaction, leading to it being exothermic. It is clear that there are two distinct regions on the binding energy per nucleon curve, associated with two different nuclear reaction processes, nuclear fusion and nuclear fission. Nuclear fusion is the combining of two light nuclei into a heavier nucleus. This is the process which provides stars, such as Sun, with their energy source. Nuclear fission is the splitting of a heavy nucleus into two lighter nuclei. This is the process which provides current nuclear power stations with their energy source. Nuclear reactions can be shown in a Feynman diagram, where the time will go from left to right. The matter particles will be represented by straight lines with arrows. Particles will have their arrows aligned with the antiparticles will have their arrows pointing in the opposite direction, although they are still moving in time towards the right. The bosons, which are the exchange particles, will be represented by wiggly lines. The particles interact only at a vertex. To the left of a vertex is the in state or before. To the right, the out state, and it's after. A vertex must have at least two straight lines attached to it and no more than one wiggly line attached to it. Each vertex has one arrow pointing in and one arrow pointing out, and the conservation laws apply at each vertex. Now we are going to talk about the structure of matter. The elementary particles that make up hadrons are known as quarks, of which there are 6 different types called up, down, charm, strange, top, and bottom. There are 2 types of hadrons: baryons, composed of 3 quarks, examples are the proton and neutron, and mesons, which are composed of a quark, anti-quark state. In total, there are 6 leptons: the electron and electron neutrino, the muon and muon neutrino, and the tau neutrino. All the neutrinos have a mass that is small but non-zero. Instead of force fields, particle physics describes forces through the exchange of particles between the objects experiencing a force. Each fundamental force has an exchange particle or particles. In this table, we can see how the four fundamental interactions by describing what fermions act on and which exchange particles mediates the force. All the elementary particles discussed here each form a part of the standard model in physics. The quarks and the leptons that make up matter, the exchange particles that mediate the fundamental interactions, and the Higgs boson that determines a particle mass. The standard model can be seen in the following graph. Albert Einstein realized that the only way these results can be explained is if light travels in discrete energy packets known as photons. Each photon has a specific amount of energy that exactly depends on the frequency of the light. Below a certain frequency, a photon does not have enough energy to completely remove an electron. Increasing the brightness of the light only increases the number of photons, nor the energy, so no matter how bright the light, no electrons are emitted. Above a certain frequency called the threshold frequency, all the photons have enough energy to completely remove an electron. Any remaining energy from the photon is transferred to the electron as kinetic energy. We call the amount of energy needed to completely remove an electron from an atom the work function. And this was the video on nuclear physics.